All right, welcome everyone. In this video, we're going to continue our analysis from our previous video in which I introduced the utility called Detect It Easy. So if you haven't watched the video, I would encourage you to take a few minutes, go back and re-watch that. As you can see here, I have Detect It Easy open, and so I'm just gonna touch on a few of the high points as we begin to transition our analysis from this sort of high level, let's understand or try to understand what's going on, into getting into more of the details here. This will likely be a multi-part video because there's a number of topics that I want to cover, and I don't want to get one single video to be too long. Okay, so with Detect It Easy, a couple things that are really going to stand out here for our analysis. First, we had no recognizable packer detected here. So all we have is the compiler. If we look at the entry point, we have an entry point of 402.851. And you'll want to keep that number in mind, that address in mind, as we transition into IDAPRO here in just a few seconds. We can also look at the memory map. You can see that we have a section, the text section, at an address of 401.000 with a size of 2200. So if we add that size to the address, we'd have something like 403.200, which means that our entry point, 402.851, falls within that section. So more or less what we were expecting or anticipating based off of our discussion in the previous video. At this point, we could also look at the entropy, and you'll see the text section, which is at a kind of a low address in terms of the binary file as well as the virtual address space that it's going to be loaded into. And we're suspecting that the data section here is likely where our packed, our compressed, our obfuscated executable content is coming from. Now, one thing I really want to stress before we get into the analysis here with IDA is that there's multiple ways that we can look at any particular file. And in this case, usually, I'm not looking at trying to understand every single detail as I go into the static analysis, as I go into using IDAPRO to look at the layout of this unpacking mechanism. There is a tendency then, I think, for a lot of folks, especially that are relatively new to it, to feel this compulsion to go through and analyze every single bit of the file. And I think even really experienced REs, one of the things that we all like to understand all of the details. I like to know how everything works. However, that's usually not a practical thing because there is a lot of code, there's a lot of nuance, there is a lot of things going on in even in just this simple unpacking mechanism, that you may not have the time, you may not have the need to get into all those details. And so what I want to show here is how I tend to try to look for the key points in the unpacking, try to not get lost in those weeds, in those details, and just get to the next stage. Because let's say in this case, I want to look at the stealer. I want to look at what the stealer's doing, maybe what software it's targeting, how it's communicating, what is it capable of. I don't necessarily need to know all of the gory details of how it's unpacking itself. I might, but for this video, I don't want to get lost in those details there. Okay, so let's minimize. Well, actually, let's refresh, right? Entry point. I said that's important. We'll see this in a minute. 402.851. Okay, now when it comes to analyzing our sample, the file information that we have from tools like Detect It Easy, they'll indicate, it should be, well, you can see right here, PE32. It's a 32-bit executable, which means I'm going to use the 32-bit version of IDA. You can drag and drop on the icon if you have the icon on your desktop. I have a licensed version, but the free and the demo will be very, very similar. If you want to just double click and open, you'll have a few GUIs that will allow you to load the file or drag and drop into IDA's main interface. So there's a number of ways that you can get the file loaded. At this point, we can go with the default. And I'm going to close the output window below just because I have things a little bit, font sizes and everything will be a little bit maximized here to save on some real estate. So your default view, you'll have functions, all of the identified functions off to the left with your functions window. You'll have an overall graph view, overview of the function that you're analyzing. And then of course in the window, you'll have your disassembled instruction. Now, IDA does provide a decompiler if you purchase it. I think it provides an online decompiler now on the free version. The decompiler will give you something that represents, something closer to C. I don't recommend using it right off the bat because I think it's still important, especially if you're learning to understand the assembly. And then, of course, as you get more experience and understanding, move into leveraging or relying on that decompiler to help speed up your analysis. So we're not going to worry about the decompiler in this video. Something that I often find myself doing is enabling line prefixes. So if you go to Options, let's just do that over. Options General, line prefixes. Then in this graph view, this will tell us what address that the instruction that we're investigating will be located at. So this uses the default image base, 400,000 hex. We know that the text section, which is where our code is going to begin executing, will be somewhere in that text section. That section began at an offset of 1,000 hex. So the fact that we're somewhere, in that section makes sense. Now, IDA has identified this as WinMain, but this is not the address that we were, that I was. Right, if we go back to Detect It Easy, you'll see the entry point is at 402.851. So why the discrepancy? Why the difference? Well, what we can do in IDA is you can use the X key, and that will provide you cross-references. That will bring up a listing of any location within your IDA database that references the location that you're looking at. So in this case, I'm looking at cross-references to our WinMain function. So basically any place that's calling WinMain. Well, this is the main method, or at least it appears to be. It is, though. So it makes sense that that's only going to get called once. So we can follow that cross-reference to this function. So this is where main is called. And we'll use our graph overview to go to the top, look at the cross-references here, and we'll follow that to the start. And here you see 402.851, 402.851, right? There's our entry point. So the entry point is defined as where the code begins execution, yes, but because this was compiled with Visual Studio, go back and look. Yep. Well, Microsoft Visual C, C++, it adds this additional compiler-generated code between where the start is and where the actual entry point is, right? And so that's a very important, thing to identify, because if you, let's say we started analyzing code in here, we might be analyzing we're analyzing compiler-generated code, and that's more than likely not something that we're interested in. Okay, I'll hit escape. Escape just lets us go back, and that takes us to WinMain. So now what do we want to do? Where do we want our analysis to go? Well, we can see some very clearly recognizable strings here. Virtual alloc, virtual alloc EX, kernel 32. And this tells us a couple things. One, it appears as though it's not obfuscating the strings that it's using. And that's something that's very commonly done. Right? Strings are important, function calls are important. And so those are oftentimes obfuscated at all levels, but particularly at these early stages to make our analysis more difficult. Virtual alloc and virtual alloc EX in particular are APIs that are used to allocate memory. So very commonly seen with the unpacking process is the allocation of memory so that the unpacking logic can maybe jump to some shell code to continue unpacking, or use that memory allocation to place the unpacked code or unpacked executable into. So we could trace these references. One thing we have to keep in mind, though, is that yes, this is likely a very limited set of logic, and most of this is probably pertains to unpacking, but this could be junk too. There could be instructions and code here that has absolutely nothing to do with the unpacking process, and it's just there to throw us off. So the way I think about it is unpacking is largely a one-way process. In order to get to the thing that that this was designed to execute, it only needs to get to that point. It needs to run through the unpacking routine, the unpacking logic, and then transfer control to that executable. So with that in mind, I tend to look towards the end of functions to see how they return, what they call, and look for any sort of abnormalities there, any indication that it is a one-way flow. Well, this last basic block has two calls. a call to a subroutine 401720, and then a call to exit. Well, we know that's too far, right? If we've gotten to the point where it's calling exit, then the program is terminating, and likely it's delivered whatever that next stage functionality it intended to do. So I'm going to start with the call right before that. We can right click and look at cross references. All right, so cross references are an important thing when performing reverse engineering. So if we look at cross references from, what this will do is this will generate a graph of all of the cross references, all of the function calls from that function. So this tells us, kind of immediately a couple of really important things. One, it gives us at least a cursory view into the complexity of the logic in this function. So if I'm about to go into this function and start analyzing it, I can see that there's quite a few function calls. It's not overwhelming. There's not thousands of function calls, but there's still quite a bit. So it might not work necessarily to just, navigate into this function and just start kind of picking and choosing different function calls and jumping into them and trying to figure out what's going on. So we want to be careful there. And this function overview, this cross-reference graph, helps us to kind of set that stage oftentimes. In this case, it also provides pretty good insight because it's highlighting with this purple blocks API calls that are made. So here we have create process, then set thread context. I'm going to zoom in a little bit more. Then set thread context. Then as we move to the right, get thread context, resume thread, exit process, write process memory. So those are all of the APIs necessary to perform process hollowing. And process hollowing has a number of variations in terms of how it's accomplished, but one of the primary is that it loads a process using a call like create process, and then it grabs that context of that process that just essentially saves the registers of that process and can modify that as well as write and replace the memory inside that process before resuming the thread. So this gives us pretty good insight in that we're most likely on the kind of on the right track here for unraveling this packer. Now I might, before I've done this, I might have actually looked at the analysis in a sandbox, say triage or any run, to see, because if I see another process being created, I can you can study the process tree, you can study the API calls, and maybe by looking at that behavior and that behavioral analysis, you can suspect that process hollowing is about to occur. That way, when you go looking in the binary, you can look for that evidence to see and help focus where you are, what code you're actually looking at. Yeah, in this case, because the APIs aren't obfuscated and the strings aren't obfuscated, it makes it a little bit more straightforward. So we could, let's say we go to the imports and we look for create process. Well, if we double click on that, we can look at the cross references and you'll see there are two. So that's not that many. We could click on one, see where it's located, escape to go back, list the cross references. Oh, it's actually the same location. So it's only one call. So this is maybe a quicker way now of focusing our analysis. However, let's just take a look at the cross references to this function. You can see there's only one. That's a good sign. It's a call and then an XOR. We can use cross references to trace this back. And you can see we're right back to where our analysis was sort of coalescing on. So it's a couple of ways to get there, but we want to have something to help drive our analysis, because if we didn't, there's enough code here that I don't want to spend any time, and I certainly don't want you to spend any time, analyzing code that doesn't have an impact on your goals, that just is a waste of ultimately of your time. Okay, so finding this create process and now suspecting that process hollowing is occurring, this can help to kind of pick up our analysis. Well, we know that if it creates the process, then somewhere down in this location, we have to have a call to write process memory. Now, let's say that they obfuscated these API calls. Let's say that it wasn't clear what APIs they were calling, because maybe they're doing a call EAX and they're resolving a pointer to write process memory earlier, and it moves it into that register and then calls it. Well, the same fundamental approach for analyzing it remains the same. We have to identify what the calls are in order to begin to unravel what this code is doing. It just makes the approach a little more difficult. Okay, before we get here though, something stands out. There's a call to isDebugger_present, and if it determines that a debugger is attached via this test and this conditional jump, then it calls exit, right? So that's a good thing to find, because if, let's say, we're going to run this in a debugger and we're going to set some breakpoints on write process memory because that's where we suspect the deobfuscated payload is, we've got to get past this check in the first place. So we got to take note of that. I'm actually going to introduce a process for debugging that will it essentially negates this, but that anti-analysis can be present during this unpacking process. And so we do want to take note of that, because that can definitely impact the debugging that we might try to do in order to unravel this. Okay, so let's tie that all together then. And we have this call to write process memory. Write process memory takes a handle to the process that we're going to write. It takes a location in that process that we're going to write to, and a buffer where that data is going to come from. If you're not sure, MSDN, the Microsoft Developer Network, you can do a search engine, MSDN write process memory, and it'll break down all of the arguments for pretty much all of the APIs. There gets to be a gray area, and you'll run into that the longer you do this. But just suffice it to say, a lot of the API calls are going to be there in MSDN. So we want to know, and tools like IDA, and this is kind of an old version of IDA. I think I'm on 7.2 or 4 or something. It's gotten certainly better over the years at saying, I recognize a call to write process memory. I know what the arguments are. This is the handle to the process. This is the base address that we're going to write to. This is the buffer that we're going to copy data from. So we could try to trace this and say, all right, well, if the buffer, if what's in EAX is a pointer to that buffer, what do we move into EAX? Well, it could be that this call right here to 401970 returns a value in EAX, and that's the pointer to the buffer. So we can follow that. It does this kind of weird, jump. And okay, let's go back. So let's move this D word. If we go double click on that, you'll see it's not defined. So it's defined at runtime. Likely there was a call to virtual alloc or some memory allocation routine. It stored it in this global variable. This is simply a way to move that into EAX. EAX is moved into EAX. And if we go back, EAX then is ready to be pushed onto the stack. So at this point, I usually have kind of two choices. One is, do I continue to unravel this statically, or do I move to dynamic analysis? Do I move to a debugger so that I can do things like set a breakpoint on these addresses and inspect what is EAX and actually look at the content in that buffer? I'm going to opt for, in probably 99 times out of 100, I'm going to opt for the debugger, because I don't really want to have to spend my time, at least not right now, figuring out, okay, where did this allocation come from? What memory is it pointing to? How did that code go from its, currently obfuscated state to its deobfuscated state? Is it in fact deobfuscated? Well, yes, if it's being injected into a new process, it's ready to be executed. That doesn't mean, though, that we don't have another stage of obfuscation, but at least the next stage is ready for execution. And I don't necessarily want to figure out where all that came from, at least not at this point. I just want to confirm my suspicions, write my analysis is on the right track, and get that next stage PE file. So I'm going to opt for a debugger at this point, and use the debugger and IDA to kind of complement my analysis. Now, I'm going to stop the video here because we're going to transition to a new topic. And in the next video, what we'll do is I'll introduce WinDebug Preview and the use of time travel debugging in order to actually finish tracing our code, look at what's going on with this write process memory, and eventually dump our next stage PE file. So we'll pick up where we left off there.